Next. That's the easiest job. So I'm happy to introduce Baskar Ganapathysubramanian. I've known him for the last probably 10, 12 years. He works on a variety of different applications and science questions. And today he's going to talk about microstructure design using scientific machine learning.
Thanks for being here on a Saturday morning. A lot of this work is very collaborative, so I want to acknowledge several research groups who have intimately participated in whatever today. Chinmay Hegde is a faculty in computer engineering at NYU. Shamik and others are right here organizing this conference, and so Dawood, who's a former postdoc of mine, who's a professor in Buffalo. Jumping tracks from more mathematical approach what Rose was talking about. Here, I'm going to focus on a more engineering application of how can you utilize domain knowledge in designing microstructures. Right? So before that, a quick what does my group do? My group is interested in continuum scale scientific simulations, primarily focus on sustainability applications. So overarching theme is continuum transport. So we look at mass, momentum, charge, energy. So the second variable that Rose was talking about before. So we are interested in what is called phenomenological modeling. So we have some knowledge about what the underlying conservation principles are, and then we try to model this at scale. And so over the past 10 or so years, fast simulators because we want to look at control, design, exploration, and control. Right. So that's where the idea is for us to use scientific machine learning. Some of the recent applications of this is, can we look at COVID risk within classroom? So it's a classroom where several of us teach, figure out what the risk assessment of student replacement, masking, unmasking, exercise. Other work is on electromagnetic phenomena, and third work is on software. So today the focus is on looking at microstructure design, particularly in the concept of photovoltaic applications, in particular on what I call organic photovoltaic. So thin films of polymeric materials that can be actually, they are super cheap, they are flexible, they can be spray painted on. You have clothing that have caps, umbrellas that are photovoltaic materials, and so they have a very niche market. They don't have the lifetime of 20 years of temperature or cell, but they're 1,000 times cheaper. And so there's been a lot of interest among the materials science community, essentially to identify, to ensure that the efficiency, how much energy being harvested by these organic photovoltaic solar cells, at least matches relative to silicon solar cells, and that's partly for commercialization. So one of the key things that the community has realized is that the distribution of material, right? So the microstructure. So here it's a two-phase microstructure. The black voxels and the black pixels are material type 1. The white pixels are material type 2. And these are two classes of chemistries. A is what is called a donor, electron donor. It absorbs sunlight and creates an electron-free electron. And the white material is an acceptor. Essentially, it's more electronegative, so the electron can jump ship onto the other domain. And essentially, what happens is that the electron passes through the white domain to the bottom. The positive charge that remains passes through the black domain to the top. That's when we say the current has been collected. Right? And so you can clearly see that the microstructure or the distribution of the material typically determines how much energy you can harvest. Right? So if there are no clean links between, say, I take a point in the white domain, if there's no clean links, clear pathway to the bottom, then none. But that region is essentially useless in terms of energy. So the idea is that the pressing question in the community is, what is an ideal morphology? Question number one. And question number two is, how can we actually manufacture that particular morphology? And so mostly the work has been trial and error in terms of experimental design. But now in the last couple of years, people have come up with a computational approach of thinking approaches. So the basic physics here is determined by what is called exciton diffusion equation. This is an augmented form of the Poisson-Nernst-Planck equation. So you have essentially some amount of diffusion equation that says how much excitons are essentially tightly bound electron hole pairs are neutral, so they have ability to diffuse. And once they hit an interface between the donor and acceptor, the black and white domains, they split into an electron hole pair, and then you have charge transport under an upright electric field. So given a microstructure, the goal is to predict its performance. So what is the amount of current that I'm getting if I apply certain voltage, right? So like a battery. And if you think of this as a battery, how much power can I draw from the battery? And that is determined by the distribution of the voltage. So this is numerically challenging to solve. So given a microstructure, you can solve for essentially the distribution of what the electron hole pairs are, what the current you can capture in terms of the positive current and the negative current. And we have spent a dozen years now, also several PhDs in the group have focused exclusively on coming up with fast solvers for solving this Poisson-Nernst. So we started with the first PhD student in my group. It took about 8 hours to solve this on 4 or 5 nodes. Right now, after 12 years of development, we now have it to about 9 minutes per person. Right? So significant improvements. So the idea, so this is numerically challenging to solve, and so this makes it difficult to do optimization. Right? So the problem is, can I design the distribution of this pixelated morphology that maximizes my performance? If it requires that I perform for each of these candidate morphology, I perform this complete simulation. This will require tens of thousands of forward simulations that is computationally infeasible to do sequentially. And so the idea is that can we use generative models for microstructure design? Right. So people have shown, and the committee has shown, that generative models can create very realistic images, faces, and people recently have shown that you can also create a lot of realistic images in astronomy and climate science. And so the basic idea, I'm sure most of you know it. So this is teaching to the fire. Idea that this is a game where you have a generator that generates instances of your field that you're interested in this case of microstructure, and then a discriminator essentially looks between a set of experimental microstructures and the generated microstructure, and figures out if it belongs to the sample distribution or not. And once you train this well, and then you can then use the generator for creating instances of your. In this case, though, we are not going to use this model. What we are trying to do is over 6 or 7 year period between Shaumik, Chinmay, and my groups, as funded by an AlphaE DARPA project, we designed something called an invariance model, where it's an extension of a generative model, where you have a generator that creates an instance of a field, and then we have certain statistical constraints that we want this field to satisfy. And so we check to see if those invariances are being satisfied. And that invariance checker essentially feeds back to the generator. In addition to that, we also make sure that these fields are realistic. So we also have this. So essentially, it's an augmentation of the standard GAN framework, where we have a generator, an invariance checker, and
so one way that you can do GANs when you're comparing with the discriminator is to use some kind of distance, right? And then it's based on like some test functions, right? So like it's like you're comparing like how what are the expectations of some test functions. So can you build using the test function? Can you build in the invariance checker in the discriminator by design?
Good. So I'm going to talk about that. Hold on for 6 slides. Where the idea is that the test function is simple. Right? So I'm going to show an example where the invariance checker is simple. Where I check see does it have certain one fraction? Does it have certain 2 points? That becomes easy to use. But if my invariance checker is what is my I have to solve a PDE to figure out if it's satisfying certain correct. Then it becomes more difficult. Excellent question. So very quickly, I'm going to go through some of the earlier work that we have, where we show that for simple, like I once said, like for simple constraints of invariances, statistic invariances. We're able to enforce the invariances, and we see some. I'll give you some vignettes on where this actually seems to work very well. Right? So essentially, here's an example. I start with I want to create a Gaussian random field. So this is a random distribution of black and white pixels in this domain, but I insist that it should satisfy a known mean. It's the average amount of black pixels is say 0.5, and then I want to satisfy a certain 2-point correlation. In addition, so this is Gaussian random fields I can create now, right? So officers that can very easily create. So I don't need a neural network for this, right? So I have GRFs that mathematically I can create GRFs with a certain mean and certain 2-point correlation. What is difficult is for them to satisfy higher orders. So in this case, all my image satisfies a mean 1-point statistic, certain 2-point statistic, and a certain 3-point statistic. So creating microstructures that satisfy higher order statistics is a non-trivial task. So we do stochastic optimization techniques that can create these microstructures. So the idea was, could this framework essentially, where I'm creating a generator that has a lot of data that serves as a discriminator, and then I have an invariance that checks to see does my candidate microstructure satisfy a certain 1-point, 2-point, and 3-point statistic satisfy this, right? So yes.
Check that these two things are by computers and cluster of microstructure.
Very good question. So if it's a GRF, I can check. So I don't check, then not one constraint. Right? So my constraint is just that it satisfies a certain 1-point correlation, that's a certain 2-point correlation, and that's it. Yes. That is the last problem I have talked about. I am really deep in that. Like here, the only thing I care about is, can I construct a two-phase microstructure that satisfies simpler constraints, not that Baskar constraint that I alluded to. Here, all I want is, can it satisfy a certain 1-point, 2-point, and 3-point statistics? And so this framework essentially, these results suggest that it is easy for us to enforce these statistical constraints as an invariance checker, where we have a generator that creates a candidate microstructure. I make sure that my microstructure satisfies a 1-point, 2-point, and 3-point statistics, and then it matches visually. It looks similar to my data set of available data. Then we took it one step further, and this is a more complicated problem of, can I generate polycrystalline microstructures that essentially satisfy some statistics, right? So statistics here are, what is my grain size distribution, what are the sizes of the grains that are distributed here, as well as the grain size orientation. Whereas each color represents atoms that are oriented in a certain direction, so it should satisfy a certain grain size distribution and grain size grain orientation distribution. So the interesting thing that we showed is that the discriminator essentially can enforce implicitly certain constraints, whereas the invariance checker can enforce these constraints explicitly. So here it is easy for us to check the grain size distribution explicitly. So the explicit grain size distribution, but if you have enough data in the discriminator, it learns the orientation distribution implicitly. So the advantage of this generative invariance network that we found out is that if there are some explicit constraints that we can enforce, it is explicitly satisfied, and if you have enough data, learning the underlying implicit constraints that we are unable to enforce mathematically just by doing. So with that, the question is, we tried it out for a bunch of these kind of problems where the constraints are easy enough to enforce and to implement. Now we said, well, can I use the same framework, the generative invariance network, to design microstructures, right, to come into the actual problem at hand? So then it provides candidate microstructures. We want to check the candidate microstructures against a certain desired current property, right? So current voltage property. I say I want a current of say 6 milliamp per centimeter square. Does this microstructure give me that 6 milliamp per centimeter square? So how do I do that? Remember, I said that we had a full physics model that was very painful to solve. Ideally, what we could do is we could put the full physics model right here, and evaluate what it's, so solve that partial differential equation, evaluate what the current voltage performance is going to be, and then use that to figure. But the full Phillips model, I mean, the differential Phillips, perhaps it's possible to do. That's something that we're exploring. But right now, the framework is a parallel framework. It's not needed to incorporate within this. So the idea that we want to look at is, can we replace it with a surrogate Phillips? Right, that surrogate Phillips model that we built first, perhaps from a supervised framework. So the idea again is, I want to train this generative invariance network. The generator produces microstructures. The surrogate model of the physics checks to see if the physics is if a desired what is the performance of the microstructure, and then I have a set of candidate microstructures that I know are maybe manufacturable, so it makes sure that these microstructures are similar to them.
So, sorry, we have a question. So, if I know or want some property, specific property from specific material, for given known experimental results, can we design a microstructure that will satisfy or have that specific property?
Yes. Yes. So I'm not going to talk about that, but I've been working on making it chemistry agnostic. Right? So if I know certain chemistry properties of my molecules, let's say this is my mobility, this is my Young's modulus. Now, given this information into so this is where the design specifications comes, right? And then I'm going to design a microstructure that's aware of that. So if I have a low model metal or low metal, it's going to create microstructure that are smaller grains, so it's high mobility metal, so it has to create microstructure. So the first.
So surrogate model that you're saying. So do I understand correctly that the true data should satisfy some kind of need?
Yes.
So there you're essentially going to check generator is satisfying to be.
It's not only satisfying the I mean the generator gives you a coefficient field, and then the coefficient field you solve underlying PDE for an output field, and output field is post process to get out that quantity.
Output to get what?
Quantity of it. So the output field is so that's what we have. So the idea is not that this satisfies an invariance. The idea is that this is an input to a PDE, and then we solve that PDE for a certain quantity of things. So the simplest way, yes.
From the graph, I have to understand that you send the data from the true data and the generated to business circuit and business model.
No. So only that's right. So the idea is that the generator is generating some images, right?
Yeah.
And we want the images to satisfy a certain property, right? And but we also want the images to be to look like images that are manufactured, right? Because if I come down to the random image, there's no way that my experimental collaborators can say that's manufactured. Right, so that's what is this inductive bias here. So we are biasing the microstructures, the images that are created, to look like the images that we know can be.
The other generator data is other.
So yeah, it's
Just one quick question. So is it also possible, like when you are discussing about the grain boundaries and grain sizes, is it possible to optimize the different size of grains in the system and the orientation that correlate to the specific property in the material?
yes. So as long as you know if a certain grain size distribution or grain orientation has a certain output. So that's what previously we showed that we can create grains or polycrystal matrices that satisfies grain size distribution and grain orientation distribution. Now, if you're saying that given those information, I can predict some microstructural property, interrogate that and data, then we can essentially tune this, right? So if I say here's my property that I want, it's going to create a certain grain distribution and grain orientation distribution that will get you that property. So approach number one is we used a supervised learning framework to create that surrogate model. So how did we do that? So we just given a microstructure, we painfully did about 30 simulations, which took us a significant amount of supercomputing budget. So it took us about 4 or 5 months of continuously running these different 30,000 different morphologies on through this full physics simulations to calculate the correct voltage plot. And then we then use this data set, this supervised data set. Right? So you have an image and you have its property pair, right? So and then we trained a simple CNN to predict to map it to its property. And this seemed to work really good, right? So after doing a lot of augmentation, essentially you have symmetry flips, right? So up-down symmetry, left-right symmetry, all in the same microstructure. So we were able to train this this model, and we got about a fairly good performance. And this is essentially the error over our training. So now we are able to, just a reminder, right? So we're able to use this model that I just talked about in here. And so given the microstructure, it's able to quickly evaluate what its current performance is. And then we are able to then use this network, train this network, and now we have a generator that says, if I give you a design specification, I want a certain current. I want a current, say, of 3.32 milliamps per centimeter square, it's going to design a microstructure. I want a current of, say, 6.96 milliamps per centimeter square, it's going to design a different microstructure. And so we were able to validate this against the true full physics model, and we were able to show that as we turn the knob of the design exploration, we were able to get different microstructures that actually where the predicted microstructure, the predicted performance is the same as the actual full physics. So this was very exciting for us, primarily because of so one of the concerns in the material science in the organic photovoltaics community is there one candidate ideal morphology? Right? So what we were able to show from this result is that if you choose a certain value of current, I can create a whole family, different classes of microstructures that actually produce that. So this is very comforting to our experimental collaborators in that I don't have to target one particular microstructure, unique microstructure. I have the ability, flexibility to target a variety of families of such microstructures. Now how much time do you have? 10 minutes. So then we then thought about, can I get away by not doing these 30,000 simulations, a significant amount of computational budget? Can we get away with much fewer number of full physics simulations? So the idea is that, again, building on some recent work on multi-fidelity models, where you have models that you have some data sets that are full physics that are painful to simulate, and then you also have a low fidelity surrogate model that is very, very fast and easy to evaluate. So the idea was that could you train a framework that utilizes a combination of limited number of high fidelity simulations and many low fidelity simulations, right? So our target was, could we use only 1,000 full fidelity simulations? So it's a 30x reduction in the amount of simulations that we want to perform. So after taking 6 months, we can get the data we wanted in 2 days, right? And so, so this essentially reduces the computational cost of generating these expensive full fidelity simulations. So the low fidelity framework that's worked by Olga Odu was in terms of using a mechanistic model of the microstructure, right? So if I have representing a microstructure as a graph and asking a lot of graph queries to that, right? In terms of what is a certain domain pixel connected to the bottom. So that there's a pathway for charge transfer. Is it how many islands there are? What is the average distance an electron has to travel to the bottom, or the average distance the whole has to travel to the top, and so on. And so people in the community have identified certain features, microstructural features that are highly correlated with various stages of the photovoltaic. So essentially, we are able to use a graph-based model to extract out 3 or 4 of these states that are highly correlated with the performance. It does not give you the performance. It just says, if I give you 2 microstructures, it says this is better. It does not tell you the actual value, but these graph-based models tell you which one is better. And so we use these very fast calculations of these graph features as a surrogate, as a low fidelity. So then, essentially, the idea is that given a microstructure, we have the low fidelity estimates that we use all 100% 30,000 data set, and then the high fidelity information we only use about 3% of it. And so the results are, so then we train the surrogate model, which only uses 3% 33x reduction in the amount of data, and this seems to work well. So the figure in blue are the full fidelity model using 100% of the data. There is a simulation that took about 6 months of compute effort. This one is about that 2 months, 2 days of compute effort, and the results are close enough, right? So close enough to pass master. So this results in a 33x reduction in data requirements of the high fidelity simulations, and let's see how that works, right? So this is where the slide was. Okay. So we found out that it works as well as the full fidelity simulations, and then we were able to get a whole diverse range of designs. Right? You have a knob that you say, as I turn the knob of increasing short circuit current, for instance, I can get a whole set of diverse structures that satisfy this requirement. So this was recently published by led by Bernard in Nature Computational Theories. So now, when we were presenting this to our program manager at RFIE, they were very excited about one interesting thing. They said, "Can you talk about how much is the energy savings?" And so if you're doing the full fixed simulations, how much carbon footprint are you basically burning to create those full fixed simulations versus this low fidelity simulations, right? And so the carbon footprint, essentially what we showed is that if you use the high fidelity simulations, you're using so many megajoules of energy, versus if you're using the multi fidelity simulation, you're using about 30 times lower carbon footprint, right? So this is this one. So essentially 3 steps. Right? Step number 1 is what is the amount of energy required for data annotation, right? So creating the full fixed model. There we use profiling tools available in standard high performance applications. So you can figure out how many props there are, and then props to watts, and then tells us how much it is. And then we assume a certain number of forward passes of back props, energy for how much energy does it take the GPU, and that's it. And so the key takeaways from this is the following, right? If I want to design a certain morphology, it takes under a second to design a morphology with this. And second is it takes what is the total energy cost of performing this. So, finally, the theme here is start with a supervised model, like to create a circuit model. Then can you get away with lesser amount of data? And then the theme goes that can we get away with no data? Right. So, is there a way in which I can train instead of training using data to create a circuit model? Can I then replace this circuit fixed model with a neural network? It's given a microstructure, candidate microstructure. Can I solve for the full fixed etc. and equations using? So this is again work by a couple of students, Vishweet and Aditya in the group. So previously, we heard George talk about dimensional pins. These are point predictions. So you have your domain. You sample from one point, collocate from one point of the domain, and you make prediction on what the variable is. Our approach is to look at field-based architectures, where remember that I'm interested in a finite domain, but finite domain that's heterogeneous. So I essentially have a lattice. My input is a lattice where at each lattice point is a certain property, microstructure property that I'm interested in, and the prediction is essentially a field of outputs. Right? So what is my current across the whole domain? What is my whole current? And so on. So we are interested in looking at field-based architectures. And so we have had some preliminary promising success in designing these neural PD solvers, essentially to serve as a parametric LP solver. Right? So a simple example is we take an LP equation where my coefficient field nu, right, similar to the microstructure, right? It's a field. I come up with a finite dimensional representation of it. So I can represent the field either using Koopman or using Cardinal expansion into a finite dimensional representation. So this is an example, and then we train a unit. So here's my input field, my coefficient nu, and output is my solution field, and I ensure that my solution field, whatever is predicted, satisfies this equation. So I just check the residual of that for my whole complete domain, and I minimize that residual and that seems to work. Here's an example where here's a new field, non-trivial log probabilities of log of the new bit. So it varies about 4 hours of time. And this is essentially how my predicted solution looks like. This is a ground truth solution, and this is the error. Yes. The input, no. So the input, the way we sample the space is through a scale expansion function, but input to the unit is this image. Right? And the output is once it's trained, the output is this image. And then we see that one of the challenges, but when we explored physics from networks, was the imposition of say non-independence, right? So it's easy to impose Dirichlet conditions because non-trivial to impose non-independence because of the Lagrange parameter that I talked about. Right? So here, because it's a total grid-based approach, it's very natural to apply non-independent conditions, and so we see several line cuts across, and we're able to solve this strategy. Yes.
You mentioned you use variational formulation.
Yeah.
And that is doing the
This is completely no data.
Oh, no, okay. You know, UH.
No, there's no data. UH is only to check against the
Okay.
Yes. And so here's an example of snapshots. Right? So you asked about what are the input, right? So we sample from this terminal space. We create a diverse array of microstructures, input microstructures, and then we see that do the results match. And then we show that for a 6-dimensional representation of the input space, we get excellent results. So what this essentially serves as is a generalized PD solver, right? So given and generalized in the sense of this input representation space, and we sample any representation space, that gives us a field, that gives us a solution. This works in 2D, this works reasonably well in 3D, and this is where some of the recent work that we published in supercomputing, when we try to show that this works for 512 by 512 by 512. Right? So this, if I take a 512 cube simulation, this takes 20-30 minutes on a reasonably sized computing processor to run. And each time I want to try a different input microstructure, that takes me 20-30 minutes to perform a simulation. Right? So now what we were able to show is that through this notion of, and this is the link to the scaling variance that Rose was talking about, we can essentially have a multi-grid filter. So this is like transfer learning. Take a smaller unit with a 32 by 32 by 32 mesh, train this, use that training parameters for 64 by 64 by 64, use that for 100 and so on. And this, we show that the time to train this framework is significantly smaller than if you were to do it from scratch. Right, and then working with a startup company that's looking at distributed deep learning again. So we were able to show that this we are training this at scale. Right? This was solving down one. We went beyond GPUs. We wanted to look at CPU clusters because we can have access to much larger CPU clusters. And we show that this actually the time to train is significantly reduced. With that, I know Adarsh is standing here, so let me wrap up. So some concluding thoughts is that our approach is to generative modeling approaches with physics-based constraints, and the physics-based constraints can be either surrogate models that are constructed by multi-fidelity assimilation estimates, or we are trying to ideally deploy data-free neural PD solvers. There are several questions, open questions, right? So how do we address manufacturability? That's what that's natural data collection approach would be something that we'd be very interested in looking at. Other approaches to enforce the constraint, that's what Rose was talking about earlier. And then I want to conclude by acknowledging the people who actually did the work, right? So this a bunch of people, Aditya, Vishwadeep, Bernard, Ethan, Bella, Josh, and Amaya are all the people who did the hard work that allows me to come here. Thank you for coming.
We have time for like one or two short questions.
For the data generation from structure, what is the initial condition or box when you start with the
For we have showed it already, but the idea is to do that for the yes. So we use this is basically And this top and bottom is typically these OPB control and take for this purpose. Yes, so that's a too much of approximation, but ideally you want to do but we're not there. Yeah, that was my last question, but I don't know how to answer that. So that's why we're exploring options of can we design, can we choose a set of manufacturers that you know is manufacturable and ensure that all my design manufacturers are similar. That's one. Second way is to impose some manufacturing. Yes, so we've done for some people. We've done 2 companies, and I will send you the papers. Yes.
Compare the run something with PIM format useful grade. What's the meaning of that? You want to do something information you already knew how to grade so that you can do that.
Yeah. So pins require pins are not a parametric solver, right? If I'm given a coefficient field, I got to train the model again from scratch.
Yeah.
Whereas here, if I have 10,000 different coefficient fields, I can train the model once. Right? That's the yeah, because it's not a fine process. Right? I have a model.
Okay.
All right.
Sorry, just one quick question. So much can we also do the lattice of views, more like a points value or nominal coefficients,
You can do that, right? So it's similar to the question that you when you had your class. So yeah, that's possible to do. Right now we are using linear basis function, so it's just